Welcome to The Explainer. So today we're looking at something you probably used this morning, maybe without even realizing it. I mean, we usually just think of GPS as this handy little map tool that gets us to the nearest coffee shop, right? But in reality, it is a staggering marvel of quantum mechanics and Einstein's theories of relativity, literally wrapped around the entire Earth. We're going to unpack exactly how this invisible infrastructure operates, down to the billionth of a second. It starts with a pretty simple question. How does your phone actually know where you are right now? And what's absolutely mind-blowing about this is that billions of devices, we're talking smartphones, airplanes, ATMs, self-driving cars, they are all using this exact same system simultaneously, and it literally never gets congested. Your phone never has to wait in a virtual line to find its location. To understand how that kind of infinite capacity is even possible, we really have to look at the fundamental physics of the universe. Okay, consider this massive number, 299,792,458. That is the speed of light in meters per second. In the vacuum of space, radio signals travel at this exact, unyielding speed. And this constant, it acts as our ultimate cosmic ruler. Because if you remember your high school physics, distance equals speed multiplied by time. So if we know exactly when a signal left a satellite and exactly when it hit your phone, we can figure out exactly how far away that satellite is. All right, let's jump straight into section 1, the geometry of navigation, focusing on distance and spheres. We're going to see how we take that speed of light ruler and use it to pinpoint you literally anywhere on the globe. Now, this is a concept called true range multilateration. People often confuse it with triangulation, but triangulation measures angles. GPS measures distances. So here's how it works. If you know your exact distance from one satellite, well, you could be anywhere on the surface of a giant, invisible sphere surrounding it. Add a second satellite, and where those two spheres intersect, you get a circle of possibility. Add a third satellite, and those three spheres intersect at exactly two specific points. One of those points is usually deep in space or underground, and the other, that's you, standing right there on the surface of the Earth. So the geometry gives us our location. Great. But as we move into section 2, time is everything, looking at atomic clocks and GPS, we hit a massive, massive engineering roadblock. The crucial point to remember here is this. Light travels about 30 centimeters, so roughly 1 foot, in a single nanosecond. And a nanosecond is 1 billionth of a second. Now, your smartphone has this cheap little quartz clock inside it that drifts by milliseconds every single day. If your phone's clock is off by just a tiny, tiny fraction of a second, the math is going to think you're hundreds of kilometers away from where you actually are. To make GPS work at all, the satellites orbiting 20,000 kilometers above us have to use something far superior. They use atomic clocks, which keep time within 8 billionths of a second per day. And an atomic clock, it doesn't use a swinging pendulum or gears or springs. It literally counts the electromagnetic oscillations of atoms, specifically cesium-133 or rubidium-87. In fact, fun fact for you, the actual scientific definition of a single second is exactly 9,192,631,770 cycles of a cesium atom. These clocks are so unimaginably precise that they wouldn't lose a single second even if they ran for 15 billion years. But we still have a problem. Your phone definitely does not have an atomic clock in it. And that brings us to our mathematical hero, the fourth satellite. Remember a minute ago how 3 satellites give us those 2 intersecting points? Well, if we bring in a 4th satellite, your receiver suddenly gets a 4th distance measurement. It uses this extra data to solve a really complex equation that actively figures out how wrong its own cheap internal clock is, and it corrects it right on the fly. So, thanks to this 4th satellite, your basic $50 smartphone effectively achieves atomic clock precision the exact moment it connects. It's brilliant. Which brings us to the absolute climax of our explainer, section 3, Einstein and the satellites, where we're testing relativity. Because honestly, even with atomic clocks and all this brilliant math, this entire multi-million-dollar system would fail within minutes if we just ignored the fundamental nature of the universe. This sets up an incredible physics problem. Einstein's special relativity tells us that because these GPS satellites are moving incredibly fast, like 14,000 kilometers per hour fast, their clocks actually tick slower by 7 microseconds a day compared to us down here on the ground. But wait, Einstein's general relativity tells us that because these satellites are 20,200 kilometers away from the center of the Earth, they experience weaker gravity. And because they're sitting in a weaker gravitational well, space-time is less curved up there, which means their clocks actually tick 45 microseconds faster per day. So when you combine those two relativistic effects, right, you've got 7 microseconds slower from the speed and 45 microseconds faster from the gravity, you are left with this magic number, 38. The atomic clocks on the satellites are running exactly 38 microseconds faster every single day than our clocks down here on Earth. Now you might be thinking, 38 microseconds, that is literally nothing. But remember, in the world of GPS, a single nanosecond equals a foot of distance. If engineers didn't mathematically account for that exact 38 microsecond time warp, the whole GPS system would accumulate 11.4 kilometers of error every single day. Within just a week, the map on your phone would be off by nearly 80 kilometers. The entire global system would be completely, totally useless. So how do they fix it? With what has to be one of the most brilliant engineering hacks in history. The baseline frequency of the satellite's atomic clock is 10.23 megahertz. But before that satellite is ever launched into space, engineers deliberately slow the clock down to exactly 10.2299999543 megahertz. They basically bake in the relativity correction while it's still on the ground. That way, once it launches into orbit and actually experiences the time warp of space, it naturally speeds up to take at the exact same perfect rate as our clocks back on Earth. And you know, the physics doesn't even stop there. The system also has to constantly calculate something called the Sagnac effect. This corrects for the fact that the Earth is actively rotating underneath the signals while they're traveling through space. Plus, it calculates eccentricity corrections because satellite orbits aren't perfectly circular, they're slightly elliptical. This means their speed and the gravity they experience are constantly fluctuating slightly on every single orbit. All right, let's bring things back down to the ground for Section 4, Overcoming Earthly Errors. Because once that signal survives the time-bending realities of space, it still has to smash into our messy, unpredictable atmosphere. There are 3 major earthly obstacles we have to deal with here. First, the signal hits the ionosphere, which is basically this huge plasma of free electrons that slows the radio waves down in totally unpredictable ways. Engineers get around this by broadcasting on 2 different frequencies. By comparing the delay between those 2, receivers can actually cancel out the interference. Then, the signal hits the troposphere, where dry gases and wet water vapor mess with it again, requiring some really complex weather models to fix. And finally, there's multipath error. If you're in a city, the signal might bounce off a giant skyscraper before hitting your phone, totally confusing the receiver. We mitigate that with advanced antennas designed to just reject any signals bouncing up from the ground. Now, even with all those errors, a standard phone gets you within about 5 meters. That's great for walking around, but for landing airplanes or steering massive tractors, we need way better. Systems like WAAS use ground stations to broadcast corrections directly to airplanes, which tightens that accuracy to 1 to 3 meters, while local DGPS stations give you sub-meter accuracy. But the real magic here is RTK, or real-time kinematic positioning, along with systems like PPP, which give you centimeter-level precision. RTK doesn't just look at the code hidden inside the signal, it actually measures the tiny 19-centimeter L1 carrier wave itself. By locking onto the exact phase of that wave, RTK pushes GPS accuracy down to literal centimeters. It's exactly how modern tractors can plant thousands of seeds with absolute perfect spacing. So this infrastructure is incredible for sure, but it's also constantly evolving. Let's shift gears to Section 5, the future of GPS, modernization and beyond. Because, you see, GPS isn't just some static legacy system. It is heavily and continuously modernized. Back in 2010, the Block IF satellites introduced the L5 signal, which is this powerful, robust signal reserved exclusively for aviation safety. Then in 2018, we started launching the Block 3 satellites. These things boast 3 times the accuracy and up to 8 times the anti-jamming capabilities of the older models. And looking toward 2026 and beyond, the upcoming Block 3F satellites, they are going to feature laser crosslinks, meaning the satellites will actually talk and synchronize with each other directly in space, entirely bypassing the ground stations. And honestly, we really need those upgrades because GPS is incredibly vulnerable. The signals reaching Earth from space are so incredibly weak, they're about 20 billion times weaker than your home Wi-Fi signal. That makes them super susceptible to things like jamming, where bad actors just drown out the signal with loud radio noise, or even worse, spoofing, where they broadcast fake signals to trick your receiver into thinking it's somewhere else entirely. To fight back against this, the new satellites use highly encrypted military M code and a brand new civilian authentication protocol called Chimera that cryptographically signs the signals to prove, hey, this is the real deal. So, where are we going next? The bleeding edge of navigation research is just thrilling. Right now, we're looking at deploying satellites in low Earth orbit for vastly stronger signals that are much harder to jam. Scientists are actually installing next-generation optical atomic clocks on the International Space Station, which could push our accuracy down to the literal millimeter. And probably the most wild concept, researchers are developing quantum sensors. Think atomic gyroscopes that could navigate with total precision deep underground or underwater, completely independent of any satellites at all. Ultimately, GPS is no longer just a map in our cars. It's an invisible, time-bending web that perfectly synchronizes global stock exchanges, cellular networks, and huge power grids. Literally, every time you check your location on your phone, you are proving Einstein right, and you are tapping into a multi-billion-dollar quantum experiment floating in the cold vacuum of space. So, I'm going to leave you with this to chew on. Our entire modern world relies heavily on a signal that is literally weaker than a whisper, beamed from 20,000 kilometers away. What happens to our society if this invisible web suddenly just disappears? And as we master things like quantum sensors, how is the next huge leap in navigation technology going to reshape our reality? Thanks so much for joining me on this explainer today, and as always, keep wondering.